um, about the stress. And the second one is about the strain. Third one is about strain. Uh, okay, let me use a word part that would be easier. About strain. Third one I'll be discussing would be about displacement relations, and the fourth one is about stress strain relations. The fifth one is about equilibrium. So these are the topics that I'll be covering in the current this thing. So as we all know, by definition, stress, or I would say, I would define an average stress is defined as force divided by area. So let me make use of some graphs for this. If I take a picture, let's say this one, this is a bar. Let me add a text to it. This is a simple uniaxial bar, and I am fixing it at this end. This is fixed end, and I am applying a force of force equal to F. So, and let us say the properties of this is given by E is the Young's modulus, and A is the cross sectional area. So this is our uniaxial bar. So now, as per our strength of material approach, our average stress is defined as force per unit area. In fact, what I want to say that this is only true on an average sense. In fact, let us say if I change this load, and let me just copy it, in fact. Before that, let me just select it. So let me take this bar again and copy it. And apply a load of the same magnitude but each is of f by 2 and f by. So then I would ask you the question again, what is the stress in this bar? The stress in this bar again is given by the same thing, which is equals to, in the first case, case 1, it is stress is equals to F by A. In the case 2, the stress is given by F by 2 plus F by 2 are acting on the same area A. This is the second case. Similarly, there is another case I want to show. In this case, I want to apply many such things, many loads, which is like a uniformly distributed, whose intensity, it is an, I mean, I didn't draw it as uniform, but take it as a uniformly distributed load on this, which is equals to force. This is the intensity at which I'm applying, or along this width. So in this case, the stress is F by A is the force applied on a cross section with an area A divided by an area A. In all these cases, the stress is given by F by A. So if you look at it, case 1, case 2 and case 3, this is the case 1 where there is only a single point load. The stress is F by A, that's what you are saying. In the second case also it is this one, and the third case is also the same thing. Why? Because in strength of material, the definition of stress what we have studied is nothing but average stress. The average stress may be the same in all the three cases. However, the point to point stress distribution varies from case 1 to case 2 to case 3. Why? Because if I again have a look at it, this F by A is only valid beyond certain depth D, because according to the Saint Venant's principle, and these end effects would vanish at a depth D, which would be the cross-sectional characteristic length, either height or the width of the cross section of this bar, beyond which the average stress is valid. So the assumption of stress what we have studied in strength of materials should be considered as the average stress. Now when you as we grow up, we leave the strength of material approach because it's an average approach, and we want to go for the exact approach. The exact approach definition for the stress is given by, anyway, these all things are corresponding to one dimensional. So the actual definition of stress is given as limit delta A tends to 0 delta force divided by delta A. So is your definition of stress. That means, let me write it out. It is little difficult for me to write, but still I'll try to write it. So this definition of which is also called as sigma is equals to as limit delta A tends to 0 delta F divided by so this is the definition of the same stress what I have written. So the stress is as the limit delta A tends to 0 delta F by delta A is defined as your stress at any given point. So why the average stresses are not valid? Because now we are looking at a continuum, and at the continuum we want the characteristics of it at every given point, not in an average sense. So now we have to actually work with the actual definitions. The actual definition says that delta F divided by delta A is your definition of stress. Now this is what we have studied to multi-dimension. So what we need to do is, now let us look for the two-dimensional. Now if you look at the two-dimensional state of stress, then uh, before moving on to the two-dimensional, I would give you a very uh, crude example. So now let us take the same bar and apply whatever load you want to apply it. It doesn't matter, of magnitude F. But now I want to know the stresses in this inclined plane. So what is the stresses in this inclined plane? This is almost like going towards the two-dimensional, because if you look at it, earlier we were finding out the stresses in the vertical planes. These are the stresses in the vertical plane. But now we want to know the stresses in the inclined plane. The inclined plane, we need to know that the effective area is also changing depending upon the angle theta. So depending upon this angle theta, depending upon angle this theta, it would vary. So let me kind of derive it for you. So let us say this area is A, the cross sectional area. Then we know that the horizontal component, so we can just write uh, sine theta sine theta is equals to, let us say this one as the inclined area as A dash is given by A divided by A dash. That means my A dash is given by A divided by sine theta. This is my inclined thing. Similarly, force component which is acting in this can be split into the one which is acting normal to this plane and the one which is acting tangential to the plane. Sorry about my writing skills. Maybe by next class I'll try to improve it. So this is not looking like a normal, but take it as a normal component n and one that is tangential. Now, if you look at it, so this is the vertical and this is the horizontal. They are, both are perpendicular to each other. Now, and this are perpendicular to each other. So that's the reason you can clearly say that this angle will also be equal to theta. So these two are perpendicular in nature. These two are perpendicular in nature. So let me just again get back to it. So this is perpendicular to this. This is perpendicular to this. So that means this angle is same as this angle, but we know the other angle. So this angle is theta. So if this is theta, you can write that the tangential force, or now since you know the thing, you can write T divided by total force F is equals to cos theta, or N divided by F is equals to sin theta. So that means, let me re-emphasize it. So T is equals to F cos theta and N is equals to F sin theta, and A dash is equals to A by sin theta. Now if I come back and look at this picture, that means this inclined plane has a stress which has in the tangential direction as well as one in the normal direction. So then we should have two kinds of stresses. The one that is acting in the tangential direction should be the shearing stress, because this will be going in one direction, the other. on the other side. So there is a shear stress acting on it, and similar to the previous case, which is a normal stress, there is normal stress acting on it. So let us define stress is same, but we will write it as normal stress as sigma, which is equals to n divided by a dash. N is the normal force acting on that plane, and a dash is the cross sectional area of that inclined plane. That means if I know these three terms, I can write this one equals to F by A sine square theta. Similarly, my shear stress, which is defined by tau, is given by a tangential force T divided by area of that inclined plane is still A dash, this one. That turns out to be F by A sine theta cos theta. Now, let me re-emphasize what I am telling. Using these expression I substituted here, I used to define my normal stress and the shear stress on this inclined plane. This is my inclined plane. So on the inclined plane we could putting on it. This is the starting point to see that depending upon the orientation of the plane, this is the orientation of the plane with respect to the loading direction, we can experience as two types of stresses. One is a normal stress and the shear stress. So with this as the starting point, now I am ready to define what is known as two-dimensional or three-dimensional state of stress. Let me define it. My sigma, which is, now I call it as tensor, which is equals to sigma 1 1 sigma 1 2 sigma 2 1 and sigma 2 2. Sorry about my writing skills again. This is for a two-dimensional state of stress. Now, let us understand what does this component mean. So let me draw a small stress square, a square in two-dimensional sense. Now I can have a loading because of which is normal in direction in these things. Or I can have some shear stresses that are acting on this. So let me define what are these things. This is sigma 1 1. If you are not comfortable, I will tell you I use x as one direction and y as second direction. So if I write sigma 1 1, it is also known as sigma xx. This is sigma 1 1. This is sigma 2 2. This is sigma 2 1. This is sigma 1 2. This is sigma 1 2. And this is sigma 2 1. So when I write sigma I and j, where I comma j can take any values from set of 1 to 2. That will give us the entire this matrix, which is two-dimensional state. Now the first one, if you know I is the direction of the normal of the plane and j is the direction of the component's direction. That means if I take, for example, this component sigma 2 1, okay, it is acting on this horizontal plane. For the horizontal plane, the normal is given by, this normal is given by E2, and the normal for this plane, vertical plane, is given by E1. E1 is the vector. E1, E2 are the vectors. This is y vector. This is line parallel to x-axis. This is a line parallel to y-axis. So E1 and E2 are those things. So if I take this horizontal line, any or a plane, for a plane, what is the unique thing that characterizes plane is nothing but its normal. So to characterize this uniquely, we know that if you mention at that given point its normal, then you have uniquely defined this plane. So the normal of this plane is in the two direction. And if you look at this component, let me draw the axis. So this is E1 direction parallel to the horizontal is parallel to E1 direction, vertical is parallel to E2 direction, or you can simply write this is second direction and this is one direction axis. So this component sigma 2 1 is parallel along the one direction. However, the plane on which it is sitting or acting is defined by a normal which is given by 2. That means sigma ij is defined as this one as normal this is the normal of the plane, or you can write plane normal. So plane normal direction is given by I, and this is the direction of the component itself. Plane normal, and j defines the direction. That's how on a small square which is infinitesimally small, that means this dimension so this dimension is delta x, and this dimension is delta y, and this delta y and delta x are infinitesimally small, so I can write it as dy or dx respectively. So I am looking at very infinitesimal piece of a square or a piece of uh, in a planar body is a small square of a rectangle of size delta x by delta y in the limit that delta x and delta y tends to 0. That is the crux of it. And what we are doing is, so it is in line with the definition of this thing where we mentioned that sigma is in the limit delta a tends to 0. It is traction directions. Traction is the forces, and delta a is nothing but the corresponding area of the plane in which it is acting. So which would be delta x times 1, another will be delta y times 1. So this defines the two-dimensional state of stress. Similarly, in the in the three dimension 3D, it is defined as, like, now in this is a three dimension, this is a stress cube in which, first let me draw the axes. I apologize for my poor drawing skills. So this is direction 1. Let me call this as direction 2 and this as direction 3. That means a line parallel to this is parallel to E1. A line parallel to this is parallel to E2. A line parallel to these things are parallel to E3. Or simply I'll write it as 1, 2, 3. That means the total traction can be represented as stress as this is sigma 1 1, which is normal acting on a plane. This is the plane whose normal is also in the one direction. So normal is 1 and itself is parallel to the one direction. So it is 1 1. Now if I take this plane which is on the top plane, the top plane has a normal parallel to the second direction. So if I have a component acting like this, the plane has normal which is in the second direction and it is also pointed in the second direction, so it is sigma 2 2. Similarly, if I take this front plane, this has a normal in the normal parallel to the third direction and it is also acting in the third direction, so it is sigma 3 3. Now there is shear forces. Now a shear force can act like this or a shear force can act in this direction. So the shear force acting in this direction is, now this is the plane whose normal is 1 and it is acting in the vertical direction which is 2. So this is sigma 1 2. Similarly, this shear which is, it is acting on a plane whose normal is still 1 but it is anti-parallel. Parallel or anti-parallel are both the things. This is having the same parallel to each other but it is pointing in the opposite direction. Don't worry about that. So but still you can call it as third dimension. It is anti-parallel to this. That means they are parallel lines but pointing in the opposite direction. Now these are sigma 1 2 1 3. Now to counter this, you will have a shear stress which is, now the plane has a normal 2 and this is pointing, the arrow is pointing in the one direction, so it is sigma 2 1. Similarly, you can have this one which is sigma, it is lying on the plane 2 and it is acting in the third direction. This is sigma 2 3. Similarly, you can have on the front plane which is acting on the third plane in the direction of second, so it is sigma 3 2. Now then on the same plane you have sigma 3 acting anti-parallel to one direction, so sigma 3 1. So in short I can write my sigma tensor as sigma 1 1, sigma 1 2, sigma 1 3, sigma 2 1, sigma 2 2, sigma 2 3, sigma 3 1, sigma 3 2, sigma. So I haven't shown all the components. To balance this sigma 3 3, you will have on the opposite plane sigma 3 3, sigma 3, yeah. In fact, I've shown it on one single face of the plane. The other faces of the plane can also be shown, but for that it's a reflection. So the one pointing outward normal for sigma 3 3 would be pointing inward normal and vice versa. So here I have shown all the 9 components of it: sigma 11, sigma 112, sigma 13, sigma 21, sigma 22, and sigma 33, sigma 31, sigma 32, and sigma 33. So this is the 3-dimensional state of stress. Now this is, let me just kind of reiterate. We have started from the definition of a stress, which is defined as force per unit area on an average sense. Stress is, but this is on an average sense. Then we said that the actual definition of the stress, this is the actual definition of the stress, which is nothing but limit of delta A tends to 0, delta F by delta A. This is on a one-dimensional exact state of stress. Then to derive on the two-dimensional, we started with an inclined plane and then showed that the forces acting on an inclined plane is nothing but a normal force and a tangential force. Accordingly, they can split up into these compositions, and then we showed that the normal force will give you normal stress given by F by A sine square theta, and the shear stress is given by sine theta, and this sine theta cosine theta is nothing but directional cosines. Similarly, it will be seeing in this when you try to rotate from one state of E1 E2 to the other one frame of reference to the another frame of reference in a rotated transformation. Now this is two-dimensional state of stress where sigma 11, sigma 22 are normal stresses, and sigma 12 and sigma 21 are the shear stresses. Similarly, in a three-dimensional state of stress, you can see that there are 9 components of it, which is nothing but sigma 11, sigma 12, sigma 13, and so on, as shown in this figure. If you look at my thing so far, I haven't written that sigma 12 is same as sigma 21. There is a reason for it. Most people will tend to say, most people tend to say that sigma 12 is sigma 21. Then you need to understand under what scenarios people will try to do that. So let us see a force equilibrium. Just I will come anyway. Force equilibrium is not the one I require now, but still I will start with the force equilibrium. Force equilibrium says that sigma 11 in this direction should be equal to the same as sigma 11 in the opposite direction. That is one thing, and sigma 22 in the other direction should be same as the sigma 22 in this. Now let's suppose that there are also shear stress, then you can see that sigma 21 in this direction is same as sigma 21 in the opposite direction, but they are in the same magnitude, but their directions are kind of reverse. So that means addition of shear stresses will also guarantee my summation of x forces to 0. X means in the one direction. Similarly, summation of y forces y forces x forces are nothing but in the one direction and to 0. To 0. Okay. Now, but coming to the moment equilibrium, let me write it moment equilibrium. Even before writing the moment equilibrium, let me take this sigma 2 1 and this sigma 2 1. So let me redraw it again. This is sigma 2 1 and this is another sigma 2 1. They are separated by a distance of delta y. So if it is like two opposite forces separated by a lever arm would produce, here in this case, a clockwise movement m. Let me call it as m. And similarly, there is another two forces which is sigma 1 2 and sigma 2 1, which is nothing but sigma 1 2 sigma 1 2. They are separated by distance of delta x. So these are again equal and opposite forces separated by a lever arm of delta x would produce an anti-clockwise movement of m dash. Let us call it in this. So for the now, for let's write a moment equilibrium. For moment equilibrium, we need m minus m dash. I'm not yet done. Let's say I'll write it Vm equals to 0. So that has some meaning. That means that it is non-magnetic material, or let me say it's an example of it, or you can say that there are no body movements are present. So let me define what is a body force. If you have certain mass and there is gravity acting on it, that will result in, let's say gravity is acting downwards, you will have a body force B equals to mass times gravity. This is a body force, small b. But body movement, for example, is something like if you take two magnets. Let's say when I was a kid, I used to play with the magnets. You might have as well did it. So you try to bring a north pole and north pole together. You can do it. This far you can bring it. Even further also you can move it. If you try to force in, I'm talking about very weak magnets, not very strong magnets, weaker magnets. So when you try to force them together, suddenly it will flip and the north and south pole will try to join each other. So the thing that makes it flip is a kind of a movement, magnetic movement. So, or a body movement. That body movements are generally present in the polarized materials such as ferromagnetic materials. If it is non-ferromagnetic materials, you can assume, let me just finish it. If it is non-magnetic materials, you can assume that your body movements are 0. So if it is non-magnetic materials, I can bring two coins like 2 rupee coins or 1 rupee coin. You can bring it in both the sides. It's fine. So that means there are no body movements are present. That means m minus m dash has to be equals to not B, you can write it as Bm, doesn't matter, Bm, but in non-magnetic materials, this is already equals to 0. So this quantity is 0. Okay. So if this quantity is 0, you can clearly show that in this kind of scenarios, one can show that sigma 1 2 is equals to sigma 2 1. Why? Because this, let me derive it for you. So this sigma 2 1 is acting, sigma 2 1 is an intensity. It has to be multiplied with delta x to get the total force, and this is the force, delta x into 1, if you want even more precise. 1 is in the out of plane thickness, and the moment is given by, that is m is given by, this is the force, and the moment is given by delta y, multiplying the lever arm. Similarly, m dash is given by sigma 1 2 is acting all along this length. So the force is given by sigma 1 2 into delta y into 1. This is the force multiplied by lever arm delta x. So if I keep these terms in here, you can show that delta x, delta y is same, and they only tends to 0, but they are not 0. So that means in any given scenario, if Bm is equals to 0, that means sigma 1 2 and sigma 2 1 are same. So sigma 1 2 is equal to sigma 2 1. Similarly, one can even show the same thing. If body movements are not present, then this becomes symmetric. That means sigma ij is equals to sigma ji. So in those cases, this is 1 2, this is also 1 2, this is 1 3, this is 1 3, this is 2 3, and this is also 2 3. So this completes the definition of stress. So now let me move to the new thing. Let me now go to the second topic, which is called strain. Before going to that thing, I would stop here and ask for a few questions if you have any. Do you have any questions? Learned so far is defined as, so let me again open the previous thing. Divided by original length. That means, let me show the dimension. Let's say this length is given by L0. L0 is nothing but your original length. Now after it gets deformed, it may take a shape of something like this. After it gets deformed, it may become something a small change in the length can occur. So the modified this length, this additional small piece of length is delta L. If you are pulling a bar, it can change in length. So let me define my strain as epsilon is equals to delta L divided by L0. But we know that this is nothing but, again as I said earlier, this is nothing but an average strain. There is nothing called as, in true, the strain is different from average strain. So in order to define your average strain, it is like this, but in a continuum sense, your L naught is infinitesimal in nature. That means you have to write your strain as actual strain is defined as tends to 0.
Excuse me, Vishwanath. Your screen is
Yes.
not.
Oh, okay. The force has been defined by delta L. Then your average strain is defined as change of length by original length, which is nothing but epsilon is equals to delta L by L naught. However, we know that the actual strain is defined as limit of delta U. Delta U is change in the length divided by delta X. This will give us a point to point quantity. So this is the definition of actual strain. So this is the one dimensional state of strain. With the similar thing, I would write a two dimensional state of strain, 2D strain, which is very much in line with our previous definition of stress. So I would write this one as epsilon tensor is equals to epsilon 1 1 epsilon 1 2. I will take symmetry here, which can also be proved at a later point, but epsilon 1 2 epsilon 2 2. Here I don't need an equilibrium to show that they are symmetric. By definition, they are symmetric because of interchangeability of the operator. So let me prove it how it is there. So we anyway first let me write it down. Epsilon I j, where I and j would take on a values from a set of 1 and 2. Now at this point of time, I'll be introducing something called as small strain. Don't worry about it. What is a small strain? Small strain. Small strain. The definition of a small strain gives us the definition between, or it is also known as strain displacement relationship. So let me see here strain relation. This is your displacement. Let me rewrite it again. So this is relative displacement divided by original differential original length. So that means your strain is related to the displacement by this definition. The definition of strain when we are writing itself has given us the original form. So this thing is also written loosely or without knowing. We generally write this one as for a one dimension du by dx. So let me rephrase it. Epsilon is equals to du by dx. So you can see that in one dimensional, this definition of a strain itself is nothing but the strain displacement relationship. It has displacement in it, it has strain in it. Now the similar thing when I'm making for the two dimension, I have to write this one as the strain displacement relationship as epsilon 1 1 is nothing but, again let me draw a small cube, and this cube got deformed into, let's say, this small cube under the deformation. So that means my change in length delta u1 is this one divided by delta x1. So I can write it this one as dou, because it's a partial, dou u1 divided by dou x1. So I sometimes I interchangeably use as this y or second direction, anything is same. This is x or also one dimension. So the displacement along this direction is given by u1. The displacement along this is given by u2. So epsilon 1 1 is given by this. Similarly, epsilon 2 2 is given by the displacement along the vertical direction, which I am not drawing a figure, but can be written as 2u 2 by dou x2. This is not a rocket science. All I did was I just copied my one dimensional state of strain, the same thing. Instead of full derivative, I made it partial derivative. Since there is only one direction, that is u, however in the two dimension you have u1 and u2. So this has become u1 and this has become x1, u2, x2. Corresponding epsilon 1 1 something has been defined. However, how do you define your shear strain? So let us define the shear strain. These are the normal strains. Let me define the shear strain. Now, under the application of the load, this guy gets deformed into just take it like this for granted. So if I have to define my shear strain is nothing but change in the shape. So let me tell you again, shear strain helps shear strain helps in helps in quantifying change in shape, whereas normal strain helps in quantifying the change in length or a dimension. Sorry about the spelling mistake. Change in length. So now how do you measure the change in shape? So epsilon 1 2 is nothing but an average change in shape is measured by this theta difference. So this change and this change in an average sense. So that is 1/2 of this angle and that angle. So what would be this angle? You can see that this length is delta delta u1 divided by delta x2. So let's say this is your delta u1. This length is more or less delta x2 plus, and this is delta y2, and this length would be more or less delta x1. So delta u2 divided by delta x1 in the limit delta x1 comma delta x2 tends to 0. So that means average change in this angles will give you your shear strain. That is nothing but 1/2 of dou u2 by dou x1 plus dou u1 by dou x2. Okay. Now I want to define epsilon 2 1. Epsilon 2 1 by the same definition can be defined as 1/2 dou. So did I write it in the reverse manner? Yeah. I actually interflipped it. This term is the first one, and anyway, let me rewrite it as per this definition. So delta U1 by delta X2 plus delta U2 by delta X1. Now, if I interchange this one to this place in the first term, addition can be interchangeable. A plus B is equals to B plus A. By this definition, it is same as equals to epsilon 1. So that's the reason I have taken here as epsilon 1 to epsilon 1 2. That means these are same. I haven't defined epsilon 1 2 different from epsilon 2 1 because in the operator relationship, this inter-exchange will lead to this one, which is nothing but definition of 1 2. So in that case, epsilon 2 1 is nothing but epsilon 1 2. So similarly, a three-dimensional state of stress, of the strain is defined in the similar lines as epsilon epsilon 1 1 epsilon 1 2 epsilon 1 3. By symmetry, I am making use of symmetry 1 2. I told you earlier why I am using the symmetry epsilon because of operator interchangeability. Epsilon 2 2 epsilon 2 3 epsilon 2 3 and epsilon 3 3. The easiest way to remember this definition is in for the 2D or 3D, epsilon I j is equals to 1/2 dou u I by dou xj plus dou u j by dou x I, where I comma j will take on for 3 dimension 1 2 and 3, the set of 1 2 and 3. So this defines the two things what we have stated. So today, so far we have completed stress, strain and the strain displacement relationships. The next thing we have to do is the stress strain relationships and the equilibrium. So to summarize it, let me again tell you about the strain and the strain displacement relationship. The strain in an average sense is defined as change in length by original length, but the actual strain definition is delta u by delta x in the limit delta x tends to 0. So for one dimensional state of strain, it is epsilon is referred as epsilon is equals to du by dx. So when it comes to two dimensional state of strain, I am defining a small strain as an assumption and I am writing epsilon 1 1 1 2 1 2 2 2 as my strain tensor. Whereas in this case, two dimensional, my a and j will take 1 to 2 from the set of 1 to 2. Now when I am defining my normal strain, similar to the stress, when you go to two-dimensional, there is one which is normal strains and the other which is shear strain. The normal strain defines the amount of change in length in that corresponding direction. So it is very straightforward, similar extension to the previous thing. So it is dou u1 by dou x1, dou u2 by dou x2. However, if you want to define the shear strain will capture in quantifying the shape change. The shape change is obtained by measuring this deviations or the angles. Since the angles are small, you can approximate tan theta as theta, and then you can write it your theta as tan theta, and that means this is the thing. And I want in an average sense, that means this is the half of it. So that's the reason I take it in the corresponding manner, and by the definition of it and commutability condition of addition, epsilon 21 is same as epsilon 12. The same thing is extended towards the 3 dimension, and it is written as in this manner. Now let us see for a normal thing. I and j, let's assume epsilon 11. In this case, for epsilon 11, my I comma j all are equals to 1. That means you put dou u1 by dou x1, dou u1 by dou x1. This is 2 times of dou u1 by dou x1. 2 and 2 gets cancelled out, and it will give you epsilon dou u1 by dou x1. Let me write it out for you. 1/2 dou u1 by dou x1, because I is 1, j is 1, plus j is 1, so dou u1 again by dou x1. So if you look at it, the first term and second term is same, that is it is equals to 1/2 times 2 times of dou u1 by dou x1. That is nothing but dou u1 by dou x1, which is similar to the state of definition which we have given. Now similarly, let us see an example of epsilon 2 3 2 1 by 2 dou u2 by dou x3 plus dou u3 by dou x1. This is the shear strain definition, which is same as, sorry, I'm sorry about it. This is not 2. This is not 1. This is 2. So this is same as epsilon 3 2. So this completes the second topic on the second and third topic of strain and strain displacement things. So let me save it. Now the third thing what I want to go and share is the equilibrium conditions. Third one is also done. Now the next thing is the relation between the stresses and strain. I will try to do it in 1-dimensional predominantly, and then from there I will build it on the 2-dimension and the 3-dimension in nature. So for that, let us again take a new sheet and open the stress and so the fourth topic of the day is stress strain relationship. I think most of you by this time might have looked at the stress strain relationships of a uniaxial bar. Let me rewrite it for you guys. This is, let's say, strain, this is strain, and this is stress. And the stress strain relationship looks something linear, and then you'll have some upper yield point, lower yield point, something like this. So let me redraw it again. It is linear straight line. I'm sorry, I cannot draw a straight line, but let me put a straight line first. And then from here you have an upper yield point, lower yield point, and then a rupture point. So we might have studied this stress strain curve uniaxial stress strain curve. Let's first suppose say it's a mild steel. This experiment you might have done in your strength of materials in the first or second year of your SM lab. So initially it's a straight portion, and this is the point which is called as proportionality limit. And then there is another limit. There is, which we call it as elastic limit, and there is upper yield point, lower yield point, and this is maximum stress called UTS or ultimate tensile strength, and this point is your rupture point, beyond which it will not take any further load. Now we know that proportionality limit was, I mean, this goes back to Hooke's law, where he said that your strain, which is nothing but, and your stress are proportional to each other. That is, they are varying linearly. That's what even the figure says. This you obtain by taking a dog bone specimen and under a uniaxial, you pull it up, take the loadings, and measure the strains and forces and stresses and strain, or displacement and the forces, get your stresses and strain and plot it. You'll get a typical curve like this. Now Hooke's law states that your sigma is proportional to strain. How it is proportional to the strain? It is linearly proportional. So the power of it is 1. In fact, the power in which it is proportional is then this is nothing but stress is linearly proportional to strain. And what did we do to remove this proportionality and we want to write an equation? We started writing it in this fashion. It's nothing but sigma is equals to E times epsilon, right? So this slope is nothing but, I can write it as E, or I can write, let me write it in a different fashion. Let me put it as 1, this one as E by 1, which is nothing but E. So, or in fact, without knowingly, what we have written is nothing but E is so if this is your sigma and if this is, let me take a sigma value, let this be a sigma, a strain value of epsilon. So y is nothing but sigma, x is nothing but epsilon, will give you E by 1, because this slope is same as y is E and x is 1. E by 1 is same equals to sigma by epsilon. So without knowingly, what we have done is we have established a relationship between kinematic variable, this is your kinematic variable, also known as strain, and to the kinetic variable. Kinetic means that deals with the forces. So in an average sense, we can write sigma is nothing but, this we know that in an average sense, F by A and this is a kinematic variable which we defined earlier as du by So if I bring everything together, so far what we have learned, I can write F by A is equals to E times du by dx. So either if I take this relationship or if I take so this is this is a relationship that is relating force and displacement, because this is the force and u is the displacement. This is a force displacement relationship, while this one is a stress strain relationship. So there is difference between a force displacement relationships and the stress strain relationship. In a macro sense also we can come to similar kind of a definition. We'll do that in a while. So let us come back to this thing. In most of the places here we'll only restrict ourselves to the up to the point of elastic limit. That means up to this place, up to this place, this is this side, this side is our elasticity, and we try to focus everything in towards the elastic side. After that we have elastoplastic relationship, which is not part of this scope, so we'll not do it. So here when we removed our proportionality, we introduced a kind of proportionality constant called E, and that is nothing but your Young's modulus. It is called Young's modulus. So, and this defines the relationship between the stresses and strain. So, this is what is called linear elasticity. This relationship is also known as linear elastic relationship. This is valid for linear elasticity. Since the scope of the studies is restricted to linear elasticity, we'll stick to this definition as far as possible for the rest of the course for the one-dimensional state. Now this is for valid for 1D. Okay, this statement is valid for 1D. However, now when it comes to 2D or 3D, how does we write a stress-strain relationship? So then I will try to invoke, this is the same Hooke's law, but in a something different sense. I call it as generalized Hooke's law. So when I take generalized Hookes law, that means I can write it my sigma, instead of one component I have multitude of components, sigma ij. That means depending upon I and j, if it is 2D I have 3 components using symmetry. If it is 3D you have 6 components. So sigma ij is proportional to, let's say, epsilon ij. Is this right? Is this right? No, this is wrong. So we have to write our sigma ij is proportional to epsilon k l. If I say sigma ij is proportional to epsilon ij, that means sigma 1 1 is only proportional to 1 1 and sigma 1 2 is only proportional to 1 2. It is strong. By saying sigma ij is proportional to epsilon kl, we mean to say that any of this 6 independent, for a 3-dimensional case, any 6 components of stress is a linear combination of all the 6 components of strain in the 3D case. So the meaning of it is, in 3D, any stress component is linearly proportional to all the 6 independent strain components. That's what we say. So that means when I remove the proportionality constant, I can write my sigma I j is equals to C I j k l into epsilon k l, where my I j k l will take the set all the values from 1 to the highest dimension. Highest dimension is 3. So 1, 2, 3. It can take any of these values. So that means this is still, I am talking about the behavior of the material which is lying on the elastic part of it. In order to define this elastic part of the things, the number of proportionality constants in a 3-dimensional sense would be, let us count. This can take 3 values, j can take 3 values, k can take 3 values, l can take 3 values. So it is 3 into 3 into 3 into 3. By ignoring symmetry at this point of time, I can show that I need 81 material constants to define the stress strain relationship. However, if it is one dimension, we showed that 1 is enough. So here I'm not using, in the 3-dimensional sense, I'm not yet introduced something called as directionality. One can show that if I assume isotropic materials, then two independent constants are sufficient to describe the material behavior. But here I need 81 material or 81 independent constants are required. What is isotropy? That means at any given point, in any direction I pull or compress, in any direction the properties are same. Any direction. This is directional property of the material. No matter which direction I choose, if the response is same, then it would be like this. So let me summarize it because we are coming to the end of the class. So this is your kinematic variable strain and this is your forcing vector. So in fact, if I have to show you, we have to write epsilon in one dimensional things is given by sigma by E. So let me cut it here. The same thing. This is your input parameter. Input or forcing function. Input or cause or force. You can call it by any name. Whereas strain is also called as strain response output or caused. So you took a body and applied certain amount of cause on it that result in some response or output is called strain. And how your input and output are related is through a relationship called stress strain relationship, or also known as, this relationship is also known as, this kind of relationship is also known as constitutive response. This constitutive response is a material behavior. Okay, so let me summarize it. Today what we have done is we studied about the definition of average stress, actual stress, one dimensional, two dimensional, three dimensional. Similarly, we have derived the strain definition for 1D and then showed it for 2D and 3D. Eventually, we also showed there is a relationship between the stress and the strain. Then we started doing the stress strain relationship. First we defined stress, then defined strain, and then we are bringing up this relationship using the our standard stress strain curve. Within the elasticity, we showed that it has this kind of linear response based on Hooke's observation for 1D, and then we extended the same thing for the higher dimension. Since the class is getting end, we will continue in the next class and I will break at this given point of time. If you have any questions, please let me know.